Swayam Prabha. Digital India. Educated India.
Good morning. Today I'll discuss on gas turbine cycle analysis. Regarding the contents of the lecture are Brayton cycle. I'll derive the expression for specific power output and efficiency, and then I'll derive the condition for maximum work output. With respect to gas turbine cycle analysis, I'll initiate the discussion with ideal gas turbine or aircraft propulsion cycle. The cycle analysis is very useful to find the upper limit of performance of individual components. Let's concentrate on ideal cycle. The following assumptions are made with respect to an ideal gas turbine cycle. What are those assumptions? They are: working fluid is a perfect gas with constant specific speed. Further, we assume that the compression and expansion process are reversible and adiabatic. That means they are isentropic. Further, there are no pressure losses in inlet duct, combustion chamber, heat exchanger, intercooler, exhaust duct, and the ducts connecting between components. Further, the mass flow is assumed constant throughout the cycle. The change of kinetic energy of the working fluid between the inlet and exit of each component is neglected. Further, if the heat exchanger is used, it is considered perfect. So these are the assumptions for an ideal cycle. Let's initiate the discussion with simple gas turbine cycle. The ideal cycle for the simple gas turbine is the Joule or Brayton cycle, and it consists of a compressors, combustion chamber, turbine, and the generator to produce the power. The air is compressed in the compressor, and then it is pushed to the combustion chamber where heat is added and its temperature increases. So thus high temperature and pressurized gas is expanded through the turbine and it generates power. That power is used to drive the compression and also to drive the generator to produce the electricity for a simple gas turbine plant. The ideal cycle of a simple gas turbine is represented in TS diagram by 1, 2, 3, 4, and 1, where it comprises of the following processes, such as the process 1, 2 represent the isentropic compression in the compressor. 2, 3 is the constant pressure heat addition in the combustion chamber. 3, 4 is the isentropic expansion releasing power. and 4.1 is the rejection of heat at constant pressure, which closes the cycle. Let us carry out the performance analysis of a simple gas turbine plant. As I have expressed earlier that this is the TS diagram of a simple gas turbine plant where 1, 2 is the isentropic compressor, 2, 3 is the constant pressure heat addition, and 3, 4 is the isentropic expansion. Thus, considering the isentropic processes, I can write the compressor work per kg of air is equal to H2 minus H1. H2 being the enthalpy at the exit of the compressor, where H1 is the enthalpy of air at the inlet of the compressor, that is equal to Cp into T2 minus T1. Similarly, turbine work per kg of air can be given as H3 minus H4, that will be Cp into T3 minus T4. Heat supplied would be per kg of air H3 minus H2, that is Cp into T3 minus T2. Thus, cycle efficiency can be expressed as eta net work output divided by heat supplied. So, turbine work minus compressor work divided by heat supplied. So, I have expressed as Cp into T3 minus T4 minus Cp into T2 minus T1 divided by Cp within the bracket T3 minus T2. Here, as I have told, Cp is considered constant, but in reality Cp is a function of temperature that I will express later. Thus, eta can be expressed as 1 minus T4 minus T1 divided by T3 minus T2, which can be expressed as 1 minus T1 by T2 within bracket T4 by T1 minus 1 divided by T3 by T2 minus 1. So I can express eta in the form as I have stated here. Please note that the compression and expansion process have considered isentropic. Thus, I can use the isentropic relation such as T2 divided by T1 is equal to T3 divided by T4 is equal to P2 by P1 to the power gamma minus 1 by gamma, where P2 by P1 is the pressure ratio and is denoted here as R. Thus, I can write T2 divided by T1 is equal to T3 by T4, that is equal to R to the power gamma minus 1 by gamma. So now with respect to the earlier expression of eta, you can appreciate that eta now would become is equal to 1 minus T1 by T2. Thus, it can be expressed as 1 minus 1 by R to the power gamma minus 1 by gamma. Thus, the cycle efficiency depends on the pressure ratio and gamma. Following this, I have written here that efficiency of a simple gas turbine cycle depends only on the pressure ratio and the nature of gas. Why I have written the nature of gas? Because it's depending on gamma also. Look here, the figure 2 illustrates the efficiency of a simple gas turbine cycle for different pressure ratio and also for different working fluid. So I have expressed here gamma is equal to 1.4 and 1.6. 1.6 represents the monoatomic gas such as argon, say. So look, as gamma increases, efficiency increases further. You can appreciate from the earlier expression also the efficiency of a simple gas turbine cycle depends on pressure ratio, and as pressure ratio increases, the efficiency increases. Here I derive the expression for a specific work output for the simple gas turbine cycle. Let specific work output, that is work output per unit mass flow rate, be denoted as W. So W is equal to Cp into T3 minus T4, that's the turbine work, minus compressor work, that is Cp into T2 minus T1. Now W can be expressed in the form as Cp into T1 within the bracket T3 by T1, again within the bracket 1 minus T4 by T3 minus within the bracket T2 by T1 minus 1. Now look here, T4 by T3 can be expressed as 1 divided by R to the power gamma minus 1 divided by gamma, and T2 by T1 is equal to R to the power gamma minus 1 by gamma. Thus W can be expressed as Cp into T1 within the bracket T3 by T1, again within the bracket 1 minus 1 divided by R to the power gamma minus 1 by gamma, minus within the bracket R to the power gamma minus 1 by gamma minus 1. Thus, the specific work output is the function of pressure ratio and the maximum cycle temperature T3. Furthermore, I'd like to tell you that the plant size also dictated by the specific work output. Now let us consider here a variable small t. Small t is equal to T3 by T1, where T3 being the maximum cycle temperature, which is often decided or dictated, you can say, by the metallurgical limit. And T1 is the atmospheric temperature. So thus here I like to tell you, I have introduced a variable small t. Small t is equal to T3 by T1, where T3 is the maximum cycle temperature, often dictated by metallurgical limit, and T1 is the atmospheric temperature. Here I like to express that with respect to compression, turbine parts need to withstand high temperature and thereby high thermal stress because of maximum cycle temperature. Now, further we assume another parameter C equal to R to the power gamma minus 1 by gamma. So with the assumption of small t and C, specific output W can be expressed as Cp into T1 within the bracket small t, again within the bracket 1 minus 1 by C minus C minus 1. can be simplified as Cp into T1 within the bracket small t minus small t by C minus C plus 1. So look, here specific output can be expressed in terms of maximum cycle temperature and the pressure ratio. Now again, when C is equal to 1, that means pressure ratio is equal to 1. The W is equal to 0. That is easy to appreciate. Now when C is equal to T, that also W, then also W is equal to 0. Now when C is equal to T, that leads to T3 by T1 is equal to R to the power gamma minus 1 by gamma, that is equal to T2 by T1. So you are in a situation where we can prove T3 by T1 is equal to T2 by T1. That means T3 is equal to T2. If T3 is equal to T2, that means no heat added to the cycle. That's why work output is 0. Look, figure 3 illustrates the variation of specific work output with respect to pressure ratio and temperature ratio T3 by T1. One can appreciate at small t, that is ratio of T3 by T1 increases, work output, that is W divided by Cp into T1 will increase. Furthermore, for a certain value of T3 by T1, that means for a certain temperature ratio, the specific work output would be maximum for a particular pressure ratio. Say, look, when T is equal to 2 at around this point, which I have indicated here, then the specific work output becoming maximum. So that's why this is a very important point I have written. For a given temperature ratio, the work output or specific work output becomes maximum for a particular pressure ratio. Now in the next slides, I'll show the condition when we'll get the maximum work output. Now to get the maximum specific work output for a fixed temperature ratio small t and inlet temperature T1, I can say dW divided by dC would be equal to 0. Now dW by dC equal to Cp into T1 within bracket small t divided by C square minus 1. Now if you put this part is equal to 0, then you will land to C square is equal to small t. Now what is a small t? Small t is equal to T3 by T1, and C square I have written in terms of T2 by T1 into T3 by T4. This equation will lead to T2 is equal to T4. Thus, work output will be maximum when the compressor outlet temperature and the exhaust temperature from the turbine would be the same. This is a very important observations. Furthermore, let us consider T average S be the average temperature. Let us consider T bar S be the average temperature of heat supplied to the cycles, and T bar R be the average heat rejection temperature of the Brayton cycle. Thus, the cycle efficiency can be expressed in terms of T average S by T average R. What I wanted to say that I'll explain what I have expressed earlier. I have illustrated that with respect to the figure, that's TS diagram. Now, during the heating of gas in the process 2, 3, in the Brayton cycle, temperature increases. Thus, I have considered Ts bar some sorts of average temperature of heat addition. And similarly, T bar R is some sort of average temperature of heat rejection. Thus, the efficiency of the Brayton cycle can be expressed in terms of T bar S and T bar R. So, eta is equal to 1 minus T bar R divided by T bar S. Now, if we can establish a Carnot cycle between the maximum temperature of the cycle and the minimum temperature of the cycle, the corresponding Carnot efficiency would be eta 1 minus T1 by T3. So T3 being the maximum temperature of the cycles and T1 is the minimum temperature of the cycle. Thus, one can appreciate here that efficiency of the Brayton cycle is very less with respect to the Carnot cycle. So Brayton cycle suffers from low efficiency. This low efficiency is because of high exhaust temperature from the turbine. Thank you for listening.